Okay, so last time we covered Newton's method. So this time we are going to, oh, sorry, I need to do this. Okay, so this time we're introducing a new method. So today is March 10th. So this method is called steepest descent method. So descent means going down. But when you are trying to go down in order to find the minimum point, let's go toward certain direction, which goes down the fastest. But maybe not the fastest, but no, because no one can guarantee. However, we can try to stay at the current location, try to find which direction goes down the steepest, which means having the steepest slope, largest slope going down. Let's just go toward that direction. Okay, so that's steepest descent direction, a steepest descent method. So how do we do that? Let's review Newton's method. The key equation is where you have, did I do this? Yeah, I think that's fine. So the k plus 1th x equals to the current x minus the Hessian matrix and inverse dot product gradient f evaluated at k. Right? That's what we learned from Newton's method. But in Newton's method, it's more computational costly to evaluate the Hessian matrix. Inside the Hessian matrix, we need to do a lot of second order derivatives, many terms. So the idea is, can we find a way to avoid the calculation of Hessian? Okay, so the idea, the easiest way is to keep the negative gradient direction as our moving direction. But at this time, we won't know how far we should move forward. We just know the direction. So in fact, the negative gradient direction is the steepest descent direction. So this is the steepest descent direction. Okay? And this also reminds us, from here, this also gives us a hint. Steepest descent direction may not be the best direction, because in front of for Newton's method, in front of the negative gradient vector, there is a multiplier. And you have no idea what the inverse Hessian has. There's something inside. There are some values inside. Definitely, after pre-multiplying the negative gradient, the direction changes, and also the length changes. So Hessian inverse has the ability of adjusting the moving direction and also defining a proper distance. That's how good Hessian inverse is, but it's costly. So we want to use a different method, but there will be some disadvantage. Without Bayesian, we don't know how far away we will be moving, and also there is no correction to the direction. Okay? So let me show you what steepest descent will do for the iteration. So what's happening is we introduce a parameter. So this is a scalar, basically a number. And we usually call the step size. So it's like for every steepest descent direction, we are going to take one step. But how do you define how far away you are going to move forward? We use this parameter alpha to define the moving direction. So we call this alpha as the step size. Okay? Now the issue is, how do we determine step size? Okay? So there are many ways. The way I would like to do is so-called the line search. Okay. So we need a process called line search to determine alpha k. If I know alpha k, then I know how far away I will be moving forward toward the negative gradient direction, which is the steepest descent direction. Okay? Then all I need to do next is just to iterate. Keep on finding the steepest descent direction and determine the step size, move forward to that point, and repeat this process until converge. That's basically the iteration process. Okay, so how do we do this line search? I will need now draw the flow chart to help you understand how the process is gonna look like. So basically the solution process. It's going to be a, can you say, two-level procedure? Maybe, yeah. So basically there are two levels. Okay. So now the main procedure, similar to what we learned in the past. So we will have a initial guess x bracket 0 k equals to 0. So the iteration number starts with k equals to 0. Next, we will be computing for the gradient. Okay, we will compute the gradient at the kth iteration. Then we will formulate the following equation. K plus 1 equals to xk minus. At this point, I will use a red color to show you that, in fact, alpha k right now is unknown. But we still formulate this guy, okay? So far, unknown. Okay? Now, we need to move on to a second level procedure. So the second level procedure, it's also a optimization process. It's a procedure that finds the minimum point along this particular linear direction. That's why it's called the line search or linear search. So we will move on to the line search. So like I said, the line search procedure itself is an optimization process. So what's the variable inside? The variable is alpha, because only alpha is unknown. So you need an initial guess of alpha. So this is where it's getting confusing. Because when I was a student, I was confused as well. So please pay attention. So I will have an initial guess of alpha. And it's a scalar, so only one value. Since in the main procedure, I have an iteration number of k, for the line search procedure, I will change to a different iteration symbol. I will use m. So I will have a guess of the alpha at iteration of n equals to 0, just some number. Let's say 1, 0, any number. And then the line search iteration starts with n equals to 0. So since my variable is alpha, it's a scalar. It's a 1D problem. You notice it's a 1D problem. There's no second variable, only one variable. And what I enjoy doing is to solve this by one-dimensional Newton, because Newton is quite accurate. But Newton is troublesome when it's multivariate. When there's a lot of variable, you need to do a lot of derivative. But when it's one-dimensional, it's okay. So I will use one-dimensional Newton's method to solve for the line search, only for the line search. Okay? So how do we do that? First, you basically need to have a function of the objective function changes to a format with the variable of alpha. So basically, whenever you move on to the line search, you basically plug in right here. You plug in x of k plus 1 into the objective function. When you plug it in, since the x of k plus 1 equals to a term like this, xk minus alpha k times the gradient fk. So what's unknown inside? Only alpha. So at the end, it becomes a function of alpha. I will do some exercise later on to show you. Indeed, it becomes an equation of unknown alpha, no vector sign, sorry, because it's only a scalar. So it will become a function of alpha. So right here, you will be evaluating f of alpha at the mth guess of alpha. But not only you actually need to compute the f prime and also compute f double prime at alpha m. So compute these two guys. Okay? Once you're done, apply one-dimensional Newton's method. Alpha m plus 1, this is the variable, equals to the current alpha minus f prime of alpha m over f double prime of alpha m. Do this, and then you will have a convergence check. I will just use CC for short, convergence check, right? If it's not yet converged, move on to here. If no, then m equals to m plus 1, right? If yes, that means it's converged. So if it's yes, update. So the optimal, I should say, alpha k equals to alpha optimal from the line search procedure. And which one is the alpha optimal? Basically the last one, alpha of m plus 1. So update. Here, this is like updating back to the original equation. From this procedure, you get an optimal alpha. So once you have an optimal alpha, you can obtain the x k plus 1. What do you do next? You do your convergence check in the main procedure. See if x is converged. If not, then you iterate back. So if not converged, here your k equals to k plus 1. If yes, then your optimal solution would be your last solution. Finish. So this is the main solution process. Okay? So the first time I learned about this, it's very confusing. What is alpha procedure? What do you mean by plugging? How come it's a multi-dimensional function, and after you plug in the equation, it becomes a single variate 1D problem? How come? So this is where it's getting fuzzy, and I need to show you by one example. Okay. Before I show you the example, any questions so far? It seems like you can understand. The English I'm talking about is not difficult. What I'm writing about is not difficult. But if I have a quiz right now, probably nobody knows how to do it. So that's the issue, okay? So I will show you line by line, just by solving a true problem, okay? So keep this in mind. There's a procedure like this. I will show you the notes later on, but let's go through the procedure again by truly solve a problem. So let's say we minimize x1 squared plus 5x2 squared minus 10 x1 plus 4x2, something like this. Okay. So in order to solve this, I will get the gradient first. So the gradient basically is partial derivative. So 2x1 minus 10. And also 10x2 plus 4. Okay. So this is a gradient vector. I need this for many occasions. Now, I will start my iteration. I will say my initial gas equals to, I would like to keep the numbers small, so I would just say 1 and 1, okay? Okay, now I will need to compute for the, actually, let's do it slowly. So the gradient at iteration 0 equals to, just plug in 1. So 2 minus 10, 10 plus 4. If I make mistakes, please remind me. So this is negative a and 14. Okay. Now, I can formulate the Stevens-Dixon equation. So, x of 1 equals to x of 0 minus alpha 0 times gradient f of 0. So this is going to be x0 is 1 and 1 minus alpha 0, and there's a 8. So change sign here, times 14. Okay. So what did I mean by transforming the objective function into a one-dimensional problem? When you plug in this x of 1 back to the original function, then you will see. So let's take a look at f of x1. Just plug in. So it's going to be 1 plus a alpha. I will ignore the bracket 0 for short. Just because there will be a lot of bracket 0. Just plug in, and then plus 5 times 1 minus 14 alpha. Oh, by the way, my alpha looks very much like my 2. So be aware. And then minus 10 times 1 plus 8 alpha plus 4 times 1 minus 14 alpha. You notice that it becomes a function of alpha. This is becoming a function of alpha, of 0, yeah. Right? Or just a function of alpha, right? And we will begin to do the line search with this f of alpha. So now I will move on to the line search. Since I know alpha must be positive, so I always start with initial guess of alpha equals to 0. So my alpha 0 equals to 0 and m equals to 0. Initially right here k equals to 0, right? So what I need is f prime and f double prime, right? So let me get the function first. What is f prime and f double prime? So I need to do some math here, or just do it like this. Maybe it's easier. So 2 times, actually not 2, 16 times 1 plus 8 alpha plus minus 7t alpha. I will move this guy down and up, and then minus 8t. Oh, something is wrong. I forgot about the square term here. That's why. So no. Here, so this should be minus 140 times 1 minus 14 alpha. Oh no. Yes. Right? 10. Yeah. Chain rule, right? And then minus 80 alpha, and then minus 56 alpha. Remind me if I make a mistake. Okay. So it will be easy if I do use the calculator from now on. So I will have 16 times 8 minus 140. Mistake? Did I make a mistake? Let me know. Oh. Thank you. You're right. Thank you. this. So 16 times 8 plus 140 times 14. Okay, so this is 2088 alpha, and then 16 minus 140 minus 80 minus 56. So this is this. Okay, so the f double prime would be 2088. Okay, good. Now I will start to iterate using one-dimensional Newton's method. So alpha 1 equals to alpha 0 minus f prime of alpha 0 over f double prime of alpha 0. So this equals to 0 minus f prime, so plug in 0, so negative 260 on the top and 2088 right here. So at the end, 260 over 2088, 0.1245. Okay. So you're supposed to repeat again. So the convergence check is like this. Is alpha 1 minus alpha 0 smaller than 10 to the power of negative 3? If I treat 10 to the power of negative 3 as the a small value, so the answer is no, not yet, right? So not converged. So right here, m equals to m plus 1. So m equals to 1 right now. I move on to the next iteration. So alpha 2 equals to alpha 1. Alpha 1 is 0.1245. And then minus 2088 times 0.1245 minus 260 over 2088, right? So if you do the calculation, you should get the exact same result. 2088 times 0.1245 minus 260. It's very small, so it's gonna be like this. Okay, very small number. So 0.1245 plus 0.044 over 2088. It's almost the 0.1245 plus 0.044 over 2088. It's almost the same. So for the convergence check, is alpha 2 minus alpha 1 smaller than 10 to the power of 3? Yes, because they are the same value, right? So converged. Now the alpha star equals to alpha 2, which is 0.1245. I can then update this back to the original procedure. So I will have alpha, not here, sorry, update back to here. So what do you get? x1 equals to 1 plus 0.1245 times 8, 1 minus 0.1245 times 14. And blah, 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 keep doing it. This is the basically how the line search is operating. Okay? Any questions? So the main procedure is just like Newton's method, but the only difference is that this time we are not doing a lot of finite difference to evaluate a lot of terms inside the Hessian matrix. In the example I showed you in the past, we can easily take derivative, so the Hessian matrix looks quite simple, and you can easily perform inverse. But in reality, the functions usually are very nonlinear, so sometimes it's difficult for you to perform a lot of derivatives. That's why people try to avoid using Newton's method. Okay? So this week we talk about CPC. So next week we talk about another method. It's called the conjugate gradient. The purpose of conjugate gradient is to improve one of the disadvantages of steepest descent, and also keep the advantage of steepest descent. So the advantage of steepest descent is that you don't need Hessian anymore. But later on, when I do programming, you will see it's very ineffective. The iteration procedure is very ineffective. It's doing a lot of zigzagging, like snakes. So if you have no idea where the solution is, and then you are doing this kind of zigzagging search, obviously is not effective. So next week, when we introduce conjugate gradient, it's also a method that doesn't require Hessian, but the derivation of the equation has the information of Hessian inside. So it's a very powerful method. It has some information about Hessian, but you don't really need to compute Hessian. So it will start as a steepest descent method and then provide some knowledge about the second order derivative, and then adjust the moving direction so that you can move toward the optimal faster. Okay? So let me remind you what happened in the last time, today, and next time. Newton's method, very powerful, but requires second order derivative. It's accurate, but could be costly. When you have a problem with a lot of variables, the Hessian matrix is computational costly. The inverse of it is computational costly. If you try to solve a 5x5 matrix, inverse of a 5x5 matrix, you probably forget how to do it. It's very troublesome, right? You will rely on computer to do it for you. Okay? So steepest descent, get rid of Hessian. No more Hessian. So let's just move toward the steepest descent direction. Along the direction, let's find a way to search along the line, and then the minimum point is my next position, and that defines my line's step size. And because we are doing that, we will be moving like a zigzag. I will show you why we are going to move like a zigzag. Next week, conjugate gradient. Okay, if we do the zigzag, we are not effective. So after the first iteration, the next week's method will change the direction. We no longer move toward the steepest descent direction. There will be some correction on the direction. Okay, so that's how these three methods are related. Nowadays, in the field of optimization, way too many researchers are trying to use random search. I feel like there are way too many random search. Random search is such as we call the evolutionary optimization. Whenever you see an algorithm's name, that has an animal inside. There's a evolutionary optimization, such as some kind of animals search. They try to mimic some animals' behavior in real life, and then use some mathematical description, like a ant or bee or butterfly or whatever. Way too many animals in optimization. So those algorithms usually rely on random search. So usually it's more computational costly. Those kind of methods has an advantage. They can explore the space better. So they have better chance to find the true solution, so-called the global minimum. Today we are talking about gradient-based approach. For gradient-based approach, we can only find the local minimum. We cannot guarantee we can find the global minimum. Okay, but still, the gradient-based approach are more effective than evolutionary optimization. Now, I would like to make some drawings about what happened in between Newton's method and the steepest descent method. So if you have a function, this is x1 and x2, and let's say I am doing minimizing x1 squared plus 10x2 squared. Very simple problem. So in this case, maybe not 10, maybe 9. So 3, 0 is a point. So this is 3, 0. 3, 0 gives me 9. 0, 1 gives me 9, right? So if I try to draw the contour of this function, it's gonna look like this, right? This will be the contour. Okay, and let's say you are somewhere here. So at a position of 3 and 3, if you try to compute the gradient, let's see how the gradient look like. This is 2x and 2xx1 and 18x2, right? And if you plug in 3, 3 into the function, so the gradient at 3 and 3 equals to 6 and 54, right? So it's going to be like this. A vector going upper right. Mostly up, right? But how about the negative gradient? So the negative gradient direction is here. So the red one is the negative gradient. Now you realize why we're trying to move toward a negative gradient. Because the gradient direction usually moves toward higher function value, right? The negative gradient direction moves toward lower function value. And when we perform Newton's method, what Newton did was, it tells you you can move toward this direction and goes to the origin. This is how powerful Newton's method is. So we can take a look. So the Hessian is going to be like 218 like this, and the inverse Hessian is 1/2 and 1/18, right? And if I do negative inverse Hessian dot product gradient, it's gonna be like 1/2 118 negative sign, dot product 6 and 54. So I will have negative 3 and negative 3, right? It's powerful. It directly moves 3, 3 to 0, 0. But without the pre-multiplier of inverse Hessian, if you only have the negative gradient, which is negative 6 and negative 54, how can you know you should move toward the green vector? Right? This is so that's why Hessian is good, but it could be costly. Now let's take a look at steepest descent. Steepest descent try to move toward the red arrow. So what happened when you do that? Basically, it's trying to move toward this line. So right here is the position of alpha equals to 0. So it's the line search, the alpha search basically is trying to see how further you should take the step when you move from 0, 0, when you move from 3, 3 toward the red arrow. So you can find the minimum point toward that direction. So the minimum direction, if you observe, is around here. Let me clean up a little bit. Okay. If the vector is like this, okay. So somewhere here, this is the minimum position. Because if I try to draw some, if I try to show you the contour values, if this is low, medium, and high, then over here it is low, medium, and high, right? So it's like a ball, right? So at 3, 3, you are moving towards the downward direction, and then you are going up again. So there must be a minimum. So basically, the alpha search is the method for you to find the lowest point toward that line. This is what happened about the line search. And if you Google for line search, there are many other ways. I don't like those methods. I can show you for the line search. I don't like them. I never use them. But if you are interested, there's a method called bisection. I think it's like a bisection. And the other one is a golden section. Basically, bisection is a method where you have an interval and then you always cut in half and see which half section has the solution. So if you find the first half has the solution, then cut in half again right here. And if you realize the solution is within here, then cut in half. Keep on cutting the region in half until this terminal is small enough. I don't like it. And there is a method called golden section. Similar to bisection, but you never cut at the half. You cut at a golden section area somewhere here. I think the percentage is something like a 0.632, something like that. Why do you do that? Because you can reuse the evaluation of those points. So go figure if you are interested. Okay, bisection, golden section. I'm not sure if the golden section parameter is 0.6 something. I forget the number because I never use it. I like Newton's method. Anyway, so along the line, you can use any way to find it. Okay, so I use 1D Newton. Now it's time for me to do some programming and show you this procedure in the computer. Okay. Before I do that, any questions? I'll give you guys some time to digest what happened. Okay, so let's check on the procedure, see if you have questions. Yes.
My confusion in our previous class and my today's classes, I think our results basically depends upon our initial use, right? That means the number of iterations will also depend
Yes.
upon the initial
Yes.
use. So, but mostly we are using initial use either 0 or 1 or 2, most probably. So what
Because our problem is simple at this point. And you're right. The number of iterations definitely depends on where you make the guess. But no one knows the solution. You're supposed not knowing you don't know the solution. So a guess is a guess. Like in real life, when you manufacture a motorcycle, everything needs a dimension. How do you know this pipe needs to be this thick and this long? It could be shortened or lengthened or thicker or wider. So usually for human, when we design something, we may have some experience in the past. We may design things based on experience. And those are like initial designs. So once because usually a machine has so many mechanical parts, you need to design each one of them and then assemble. And you have certain things you need to worry about, such as mechanics, dynamics, and a lot of things you need to control, heat transfer, a lot of things. So now then the physics comes in, and those physics limit your design or modify your design. So those are the things that you need. Those are the design constraints. Most of the time, design constraints, and or design objectives. Like you need to once you design a motorcycle, and you realize it's too heavy, you need to reduce the weight. Then your objective function becomes minimizing total weight. But as an engineer or the company, you still need to satisfy certain design criteria, such as the strength of this cylindrical bar has to be stronger than something. So you will have a bunch of constraints. So how do you find the lowest weight design, but at the same time keeping the satisfying the criteria? That's basically an optimization process. So if you ask 10 different designers to design 10 motorcycles, their designs won't be the same. So 10 engineers initiate the design at 10 different points. So nobody knows which engineer is lucky enough to have a solution that is closer to the optimal. Nobody knows. So, but at least we have some methodologies to help you in order to see, okay, to show you, okay, this is the optimal. So if the optimal solution exists, and if there is only one solution, supposedly all 10 engineers is getting the same solution if they are doing optimization right. So you don't need to hire 10 engineers and do 10 designs. Just hire one, do optimization correctly, and find the solution. And if he is not smart enough, his initial guess is just further away from the solution, then it's a little costly to iterate the design and then find the optimal. So that maybe after certain times of practicing, this engineer knows, okay, I should design my motorcycle at a better solution point. So my solution is closer to the optimal. Something like that. Okay. Any other questions? Okay, I think I can move on to the to the screen. So this off, this on. Oh no. Oh yeah. Okay, so Malak. Recently, I'm trying to work on an industry project. It's about optimization, and I'm trying to see why they want me to do optimization for them. Because ChatGPT is so powerful. Why don't they just do GPT themselves? Why do they pay me money and ask me to do it? So recently, I try it by myself on ChatGPT and see if GPT can truly generate uh, programming codes to do optimization perfectly. They can do probably 60% ready codes, but there's still some gap before the code to be modified to the best. So I feel like humans still have chance. I'm not sure about next year. Maybe next year we don't need our brain anymore. Let me see. I forget where I put the previous code. Last time. This is from last time. Okay. So I would like to. No, this is not from last time. This is the one. Okay. I did. Okay, good. Let me open this one. Okay, this is from February 24th. So I will use it and then modify this Newton's method code into the steepest descent code. So I will save this as today's date. So March 10. Okay. So last time we used symbolic. We plot the functions out. Initial gas, figure 1, figure 2. I don't remember why I did 2 figures. Let's see what. Let's run the code once, just to remind myself what I did. Okay. I show everything in 2D and 3D. Good. Okay. Oh, and I made some pauses. I did some pause. Okay. So this time here, the same. We will be computing for gradient. This is gradient. But we don't need Hessian anymore. I will hide the Hessian part. We don't need Hessian. We don't need the Newton's equation anymore. So only this portion is changed. So this is where we have steepest descent. main part. Okay. So you can later on figure out what's different. We need to define something called alpha, but alpha is a lot of words in computer, so I'm gonna call it just capitalize A. So my capitalized A is alpha. So right here I need to say m equals to 1. This is my line search iteration number, and then I need to get a function of alpha, right? So I first need a equation. Let me call x alpha. It's gonna be symbolic. So it will be my current x minus some unknown alpha. So I will just use A times my current gradient, because my previous code already computes gradient. Okay, let's see what this part will give me. Okay. I'm in the pause. I don't want the pause anymore. Hold on. Let me quit. I will get rid of the pause. Get rid of the pause. Okay. So run the code again. Up to here, you will see it becomes a symbolic vector, x alpha. So capitalize A is my unknown alpha. 16A minus 5, and then 5 minus 104A. A is unknown alpha. Okay? And I will be plugging in into my function. So I will call this F alpha. So it's gonna be subs and then F. So whatever x1 and x2 is, I will use my x alpha to replace it. This is how you plug in. Okay, so let's take a look. After plugging in, it becomes see? 16a minus 5 squared minus 512a plus 10 times a bunch of a's. Okay, so it becomes a symbolic function with unknown alpha. So later on, when I perform Newton's method, I can just plug in and then keep on substituting the alpha value into this function. Then I can get function value. So now I will perform line search. Basically, it's an alpha search by 1D Newton's method. Okay. So I need for the iteration process, I will need a convergence check parameter. So I'm gonna call this error, but I already used error in the main procedure, so I'm going to call this error 2. So error 2 is 100, something big. While error 2 is larger than 10 to the power of negative 3, I need to do iteration. So initially the iteration number m equals to 1. Now I need to have an initial guess. So the symbolic alpha is capitalized A, but the value alpha, I'm going to use smaller case a. And So the symbolic symbol is always there, but whenever I plug in, I use small case a different variable. So small case a keeps all the alpha values. Yes. But you need to be careful because in the second iteration, you need to delete what you have done previously. So here I will just say if exist a name, I think, or variable. Then clear a. So if I in the next iteration I will have a variable called a, I need to delete that one because in the next iteration I don't want the computer to be confused by because every line search is different. So I will delete the variable a in the next round. But in the first round there's no variable a. So I will check if the variable a exists. If it exists, clear it. If not, do nothing. Okay. Then I will say a1. This is my initial guess. My initial guess alpha is 0. Okay. Now, right here, I will do Newton's method. So what I need to do is to do the f prime. I'm gonna call this df alpha. Okay, df means derivative ones. So basically, I'm gonna substitute derivative of f alpha, and the variable is called a. Derivative of f with respect to alpha. And then after derivative, you substituting the variable is alpha, so there's a character alpha, a character capitalized a is the variable. You're substituting in. So what do you substituting in? You plug in a, the mth a. This is how you do first order derivative. So do it again. I'm gonna call it DDF. So DDF basically is derivative twice. So what you need to do is to do a DIFF again right here, and then comma a. Is it confusing? When you're done, you can iterate. So your a, basically m plus 1 equals to am minus df alpha over ddf alpha. That updates your a. So you will have a second a, the a in the next iteration. So you need to do a convergence check. So my error 2 equals to absolute difference between these two guys. And then remember m equals to m plus 1. So it will iterate. It will keep on doing this until the error is small enough. It will come out. So when you're out, you need to update your x. So your x is this one. So what is your x? Your next x. So the same equation, but this time you will update to k plus 1. And the alpha is going to be the last a you got. and basic last one. So this is how you got your x. And we're done. If my coding is right, this one will work. So let's just take a look. Oh, typo. Alpha. Okay. Zigzag. Do you see zigzag? Let's take a look. Zooming in. Zooming in. Keep on zooming in. A lot of zigzag. So Stevie's Decent is always doing this zigzag. 3-dimensionally. Let me turn on this guy. And then, not this guy. View this. Okay, and then let me see. No, plug browser. Okay, I can turn off this, and then I can do the rotation here, so you can see how it's zigzagging in the space. Can we zoom in? Keep on zooming in. In 3D, it's hard to zoom in. Now I zoom in into the wrong place. So anyway, so from 2D it's easy to see. Okay, let's see how many iterations it did. Okay, I never plot out the solution last time, so let me do that. I'm gonna, so right here, I will display, and maybe at the beginning, I will display and say, this is the line search. Okay, and then here I will display m equals to number to string, whatever m I have. Oh, before the plus one. I want to show some text information on the command window, so you can see the numbers. So when m equals to something, comma, space, then I will say alpha equals to number to string and the current a, right? And I will also show error so far equals to, so number to string error 2. Okay. If I do that, you can see a bunch of line search solution process with values. But this is only the line search part. I will do the same for the main part. For the main part, so after you compute the error, you display. Actually, I should. Every time when we jump into the while loop, I will display and say this is the the process of k equals to some number. So number to string k. I just plug in the k value. Okay, so every time we are into the loop, I will on the command window I say, oh, this is a process of k equals to 1, k equals to 2, something like that. So whenever we finally get the new solution, I will display the current x equals to a vector. So number to string, and then the current x. Current x should be this one. But our x are vertical vectors, so I need to transpose it. I need to do this, I don't know how to say it, the prime sign, to transpose it. And then also show what's the current error. So number to string, the current error. And also initially, I want to show the initial guess. So maybe right after the initial guess, right here. So display. So initial guess x equals 2, and then just the x one transpose. I need this to close it. Okay. For the x vector, because it's gonna show 2 values, so I need a bracket so it looks like a vector. Okay, I need a bracket here. Okay, do it. Okay. So, what happened? Number to string, sorry. Number to string. Okay. Go. So initially there's a guess, -5 and 5. The process of k equals to 1. We did a line search, m equals to 1, alpha equals to this. There was an error, m equals to 2. We got the same alpha, no more error, so you jump out, update x. So this is the new x. And currently, the new x and the initial x has an error of 5.3. So now move on to procedure of k equals to 2. Keep on doing this. And you can see the error was 5, 6, 0.8, 0.9, 0.12, 0.14, and until the last one, 0.0004. Small enough. Okay, converge. Okay. So this is steepest descent. Okay? Any question? Can you guys do it? Let's ask ChatGPT, see if GPT can do this. I'm curious. Okay, nowadays I realize you need to turn on this canvas. It works better for programming. Do you know an unconstrained optimization method called steepest descent method? Can you show me let me just call this SDM. Okay. Show me a SDM code in MATLAB. And for the line search, alpha search for 1 dimensional search for step size. Please use one dimensional Newton's method. In your example, you can use the following objective function. Okay, let's just copy this guy. Here, objective function. Okay. And for the initial gas, you can use x1 equals to -5, x2 equals to 5. Set the convergence criteria as norm of. I shouldn't tell him too much. Let me tell him. Norm of new variable minus current variable smaller than 10 to the power of -3. What else do I need to say? Okay, let's do it. I'm curious. See if I'm out of job. Alpha, yes. Is doing it right. Doing this right. Okay. Already finished. Copy. New project. Paste. Save. GPT 0310. Run the code. What was the solution I have? 2.9 -02. Let me see what's the solution I have. Yes. So you can learn by yourself. So let's see what he did. Okay, function. So he didn't use DIFF for derivative. He directly derived it. Initial gas, tolerance, maximum iteration. So he used a for loop. So gradient f. So plug in basically gradient. G is gradient. So if the norm of gradient is okay, yeah. If the gradient is small enough, you can already stop. Actually, the vector size of the gradient indicates the difference between the current point and the next point. Think about it. Let me show you what do I mean. Why GPT did this? I will explain to you on the on iPad. So whenever you do convergence check, and the equation, okay. So whenever you have a convergence check, you are comparing the difference between the new variable and the old variable. So if you use the new one minus the old one, basically equals to whatever you have on the right. So if the gradient is so small, you should stop. That's why the GPT code at the beginning check whether the vector length of the gradient is small. If it's small, you don't need to move. Your gradient based approach will not move to anywhere because gradient is almost zero. Okay, so that's why GPT did it. Okay, So let me go back. And then he's using a d vector to represent the negative gradient. He formulates this alpha function, x plus alpha times d. Basically, d is our negative gradient. Exactly same approach. So the f prime, basically he formulates it right here, gradient f. So basically he already formulated gradient f, and he plug in the variables right here, x plus alpha times d. And then because of the because of this is basically coefficient times d, yeah. Okay, and then double prime. He already, let me see. I think he already did something from the original function. That's why he just compute. So if I change the function right here, some of the code underneath needs to be modified. So I would say his coding is not general. It's not very general. You need to tell GPT, hey, I need the code itself to be super general. So whenever I do some modification on the top, I don't need to do anything. I need to tell him that, but I'm not going to do it. But I'll let you know what's the difference between my code and his code. So here, alpha search, basically similar approach. So just alpha new. He is using one-dimensional Newton. Alpha new equals to alpha minus prime over double prime, and then update. Convergence check. Okay, print out the result. 59 lines. He didn't do plotting. Let me ask. If I ask him to do plotting, I'm not. Maybe he will get similar lines, or slightly more. Yeah. But good enough. That's why I'm not asking you guys to do homework. Nowadays, GPT is your tutor. Okay. Okay. So any questions? Any questions about the MATLAB code? So I don't even know how to evaluate your project, because maybe GPT can help you on the project for at least 50%, and then it's really hard to prevent you doing it. I cannot say, hey, don't do it. Even I say so, you will do it. So yeah, if you get some help from the literature, from GitHub, or from GPT, that's totally fine, because that's one way to learn, get information. But once you have it, like what I'm showing you today, GPT gave me a code. Read line by line. Don't just use it. Read what GPT has done. See how something can be coded, and see if you can code it like this without help. So use it as a tutor. Remember, when we were kids, we learned something. We follow a teacher. So now GPT is another teacher. Learn from it, and then see. Like I said, from here, if I don't spend more time on GPT, it won't directly give me a general code. In my code, it's general enough. I can directly modify the objective function, and whatever underneath will be doing its own calculation. It's general code. But GPT is not giving me general code at this point. But if you keep on training it to do it, it will give you one, definitely. So yeah, that also, I feel like one tool is quite useful. Let me show you. Because if you ask GPT at this point with Canvas, if you ask GPT to modify your code, it will check line by line, and then it will modify the lines. So let me show you. I realized your code, in your code, the main optimization parts are not general for all functions. So in the future, when I modify the objective function in line, let me see which line. In line 6, I also need to modify some parts, especially the derivative parts underneath line 6. Can you modify the code into a general code so in the future I only need to update my objective function at line 6? I think he's very smart. He should be able to do it, and he will check line by line, and then let's take a look. But it takes some time. And by the way, I'm using 4.5 already. Fail? Oh no, it is. So you can see it's already changing something. Not much. So, but in order to ask the right question, you need to have some knowledge. Otherwise, you don't know how to improve it. Okay, I feel like a purpose of taking the course right here is for you to gain the knowledge of optimization, so you can ask the right question. Otherwise, before the course, you may not even know you can ask a question like this, and also a question like this, right? Okay, that's it for today. If I move on to the next method, I won't have enough time. So since I didn't take a break, so I will stop right here. And I know some of you may have questions, don't know how to ask. I will stay here for a while. You can come by, I can tell you more. Okay, see you, bye-bye. Oh, did you guys do the check, attendance check? I should. You have question? Attendance check? Okay, let me do the attendance check. Let me use this opportunity to know you more. I know 2 guys told me they are sick. So let me check everyone. So Ben's here, okay. Guan Zhong, okay. This is Kelvin, right? Kelvin, okay. This is Trent. Which character you like? Last name, Quan. You like Quan more, okay. Sorry. Tingwei is what? Jerry, okay. Even don't know my student's Chinese name, okay. Youhua, okay. I give up. Oh, Horace, okay. I don't know. Yan Hong, okay. I know this guy. No, I forget. John. Okay, you're John. Okay. Rati. Okay, good. Jason. No, you're not Jason. Jensen, you're Jensen. Okay. Boru. Okay. Sam. Yes, I know. Shen Bing, I think he's sick. He called for sick. Okay. Is this my student? Ah, I know, new student, Ray. You're right, yes. 思乔. Okay. Oh, 请假 sick. Okay. Azim. Okay. 奕晨 Okay. Ping is here. Okay. 冠宇 He dropped the course. Okay, let's just get rid of him. Okay. Okay. Ah, Wilson. Okay. 佑嘉. Do anyone know? Let me see. Someone called for sick this morning. Si Qiao and Shen Bing. So Youjia is not here. Okay. Tajel is here. And David? Yes. How about he dropped? Okay, he dropped. Okay. So Ping has no teammate. What do we do? How about can you work with David? And you walk along. You're your TA. You should do. Yeah.
I am PhD.
That's fine. Please help her. Yeah. No, I mean she's a TA. Yeah. So she can walk along, and Ping is a master. So please help her. Okay. So you are in team 10. Okay. Okay, good. Hopefully no more dropping.